Good morning, students. I'm Dr. Betty, going to take you through advanced inorganic topics. This topic will cover boranes, boranes, phosphazines. We shall look at polymeric cations and anions, stabilization of oxidation states of transitional element, and lastly, group 8 or group 18 elements. The objective of this course includes the course will advance knowledge of some materials already studied in your year 2 in organic courses, to study new selective topics of current research interest in inorganic chemistry, and also to show a variety of polymeric inorganic systems. Information on this course can be obtained from Electron Deficient Compound by Wade, The Chemistry of Nonmetals by Powell and his colleague, Inorganic Chemistry by Huhi, Chemistry of the Elements by Greenwood and his colleague, Advanced Inorganic Chemistry by Cotton and Wilson, and others. Let us look at the boranes. Boron does not combine directly with the hydrogen to form the hydride. However, the element gives a larger number of stable covalent hydride, which are called boranes. The instability of boron hydride is due to the presence of the pz atomic orbital. When we look at boron, the atomic number of boron is 5, which means it has 5 electrons. And if we place these electrons in their appropriate orbital, we have 1s2, 2s2, and 2p1. So under hybridization, one of the electrons in the 2s orbital jump to the empty p orbital, resulting into the formation of an empty pz orbital. So it is the presence of this pz orbital that accounts for the instability of the boron hydride. The stability of the diboron is due to the distribution of the bonding electrons among all its valence atomic orbitals, forming appropriate molecular orbital. There are 2 types of boranes. We have the boron of this type, BM, HM plus 4 type. An example is the diboron. An example is the diboron, where we have 6 hydrogen. And how does these 6 hydrogens obtain? The number of boron atoms are 2. If we add 2 to 4, we are going to get 6. The number of boron atoms are 5. So 5 plus 4 is equal to 9. If the number of boron atoms are 6, so 6 plus 4 is equal to 10. Then another type of the boron is the BM, HM plus 6. Now, if the number of boron atoms are 4, 4 plus 6 is equal to 10. 5 So 5 plus 6 is equal to 11, and so on and so forth. Let us look at the nomenclature of the boranes. Boranes are named by indicating the number of boron atoms by the Greek numerical prefix, di, tetra if they are 4, penta if they are 5, hexa if they are 6. We name them like the way we used to name the shapes in P5, in primary 5. And the number of hydrogen atoms is indicated by the Arabic numeral. If there are 6, we put 6, 9, 10, depending on the number of hydrogen atoms present in that borane. And this one is written at the end of the name of the borane. Let us look at the example. If the number of boron atoms are 2, we said they are called di. So the number of hydrogen is 6, the name will be diborane 6. If they are 4 and the hydrogen atoms are 10, 4 is tetra, so it will be tetraborane 10. If they are 5, it will be pentaborane 9, where 9 is the number of hydrogen atoms. This is 6, hexaborane 10, where the number of hydrogen atoms are 10. The boron are 8, that is octaborane 12. I told you we name them like the way we used to name the shapes. Remember the octagon, hexagon, pentagon, but this time instead of putting a gon, we put borane. We have said if it is 5, penta, then pentaborane 9, hexaborane 10, and so on and so forth. There is a point to note here that the hydrides of boron are electron deficient and can act as lowest acids. So next time we are going to look at the preparation of diboranes.